Well, hello 403 people. This is Dr. Keith Schubert again, here staring at the screen of my computer. And I now have pulled up Scilab. Right? Scilab's a MATLAB knockoff from France. And I use this because, well, I don't have a research license of MATLAB, therefore I don't install it. So I'm going to pull up, it's very, very similar. I'm going to pull up its editor. In this case, no, I don't want to pull up my last session because I don't want to talk about my research at the moment. We're talking about how to solve some circuits. So this is related to the circuit problem that I just did in the previous video. And basically I had two little loops inside in a voltage area. I viewed the video and it was kind of hard, even though the pen looked really clear when I was writing it. It did not show up on the video very well at all, so I'm going to do a little bit of commentary in here. We had on this one a voltage source V. In this case I'm going to set some number values here. I'm going to put 5 as its value, and I mentioned in class that I usually like to list what the values of them are, so I'm going to say V is in volts. Then I had a bunch of resistances. Right, so I had a first loop that had R1 and it had R2 and it had R3, and each one of these is going to be in ohms, and we can pick whatever we want on these, but let's say that I decide to pick, you know, R1 is equal to let's say 500, and then I'll put a comment and say ohms. Notice that Scilab uses C style and C++ style comments. So actually C++ is what I'm showing here. Let's see, R2, let's make that one, let's say like 1,000. And again, this is in ohms. And R3 will make, let's just be nice and simple. We'll make this also equal to 500 ohms. That was my first loop, right? V1 goes to R1, R1 goes to R2, R2 goes to R3, R3 returns back to V. Now we had a second loop that had R2 in common, and it only shared R2 in common, and it went from R2 to R4. So we added an R4, and then from R4 it went to R5, and from R5 it went to R6, and then it returned to the bottom of R2, which then connected to R3. So that's how we had this one set up. And we can pick whatever we want in here, but maybe I pick them to be, let's say 200, and of course ohms, and then maybe I do 400 ohms. And then I'll just do 400 ohms again. Alright, so that gives me my kind of setup. Now, I like actually writing my variables this way, where it's nice and clear, it's easy to read, it's easy to change if I want to change the circuit and things like that. And then what I'm going to do is set up the matrices that we had. Now there's a matrix and a vector that we want. The matrix A, which is our resistivity matrix. So we'll say A is equal to, and now we've got our list. So in this case, our first loop that went around, it was R1. R1 plus R2 plus R3. And then the coupling to this second loop is minus R2. They share R2 in common, and it is negative. And then we had the second set of equations for the second loop. It also uses R2 as a coupling, and then it has within itself R2 plus R3 plus R4 plus R5. Is that no? Bad me. R3 is not in here. So it has R2, R4, R5, and I should have R6. Now, if you notice what's going on here, what we've got is listed on the main diagonal are some of the resistances around the loop. So you'll see that's the first loop sum of resistances, second loop sum of resistances. And then on the off-diagonal terms, they're negative, and it's the coupling factors that go between them. So R2 is the one that couples between them, and the currents for each loop current is flowing in the opposite direction, hence the negative. So we get this lovely little symmetric matrix. Again, I'm putting in semicolons because honestly I don't want to see these things printed out. So now our second one is a vector and it's B, and we have a voltage which is V, and the second loop is passive. It has no actual source within it. All right. So from that one, we can then follow on. Awesome, and we now want to find out what the currents are, and that is A/B. Now, if you think about this, B is voltages, right? So these are our voltage elements. This is our resistance. So A, right, R times the unknowns, the currents, X equals B. What we have is resistance times current equals voltage. That's Ohm's law. So all this is saying is that my current is equal to my voltage divided by my resistance. It's another form of Ohm's law. So we can just save this up. I can go file save, and there's my research directory again. I'll just stick this onto my stuff, and let's see, we will just make a directory for 403 examples, and I'll drop it in the 403 course later. Oops. Okay, that means as well, let me make one. We'll save it right on the desktop then. 403 example 1. SCE is Scilab's extension for an executable file, and I will just save and execute this. And more than likely I have some typo. Let's see what's going on. Undefined variable V. I did indeed capitalize it. Alright, so it ran perfectly at this point. You might be like, okay, what's going on? So I want to actually take a look at what that answer was. I should actually, it's nicer, instead of using the predefined variable A and S, I'm just going to say X equals, this is our currents. Let me save that and execute. And then I can just ask, what was the answer to X? Alright, so it's telling me now, right, that I've got my currents flowing. The first one, I1, is right around 3 milliamps, and my I2, right, is around 1 and some change milliamps. You'll notice that I1 is twice what I2 is. I mentioned in the previous video we expected it to be larger, and indeed it is. This is not too surprising, because if you remember what I talked about, the kind of voltage division things that go on here, we had, and maybe it's just worse since I have the resistances here, we had the sum around the second loop neglecting element R2. So we had the kind of the R that's in parallel. Let's call it RP for R parallel. That was R4 plus R5 plus R6. All right, so 1,000, that's how I chose it. 200, 400, 400. You'll notice that R2 itself, what it's in parallel with, is 1,000. So what we have here, since these are in parallel to each other, is a current divider. Equal resistances means equal amounts of currents go down each one. Well, the amount going down this one is I1 minus I2, and this one is I2. So what that means is I1 minus I2 must be equal to I2. All right, so this is not too shocking a formula if you actually write that out. Right, I've got I1 minus I2 has to be equal to I2, right, because they're a parallel current divider. Well, if I take this second I2, I just add it to both sides, I get that I1 has to equal twice I2. And so I get 2 times I2. So that's exactly why when we get this answer out here, it makes perfect sense. I1 is indeed twice I2. That's because the way we set up these resistances forces it to be a current divider, which will actually do that. So this is kind of that sanity check that I mentioned in the previous video. You should think about those type of things. Now, since these are in parallel, essentially I'm going to get 1,000 ohm resistor in parallel with 1,000 ohm resistor. So you'll add 1 over each one, you get 2 over 1,000, which gives you 1 over 500, 1 over that, because the form is 1 over the 1 over each of the resistance sums. So I get that, 2,000 ohm resistors in parallel gives me a 500 ohm resistor. Now, R1 is 500, and this kind of net parallel one is 500, and R3 is 500. So what that means is I've got 1,500 ohm resistor net that's going on, and I have 5 volts. So if I take 5 volts and I divide it by 1,500 ohms, which is what I've got here, you end up with this 0.333, which I said if you did that on the whiteboard area, you'll get the current that goes through that voltage source, which is the current through the first loop. And that is what we did here. As a sanity check, indeed it is correct. And from the previous step, we know that the other one is half it. So if you just take that same answer and you divide it by 2, then you get this one is equal to I2. So, whenever you get an answer, you should look at it, you should think about it, and you should say, does this make sense? Can I verify it? Is this good? Is it right? How's that working? So that you don't end up with problems and make mistakes that can cause deep errors. You also find an awful lot of little silly mistakes that go on when that happens. So hopefully this has helped you out. I expect you feel comfortable with this kind of stuff. Writing simple scripts like this, it looks exactly the same inside of MATLAB. It's just different menus when it goes on, but the editor still has that ability to debug and run the code and whatever else. MATLAB's actually, I think, a little bit nicer as it goes on, but without a license of it here, I do what I got. So hopefully this gives you some idea of decent coding style as it goes on, and some sanity checks as you go through. So I wish you the best of luck with solving your version of the problems. I'll probably try to do maybe one more example talking about super nodes and stuff like that, or super loops and things, and then call it quits and move on to other stuff. So, and I'll see you in class on Tuesday. So have a lovely time. Bye.